Hello. Hello.
Hello. Good morning.
Good, good afternoon.
Oh yeah, afternoon.
morning here, morning and afternoon in your place. Okay. Are you ready to continue?
Good morning. Jaringan bagus kan? Okay, good morning. To start this event today, I hope we have a good mood, and for this event will run smoothly. I will introduce our speaker today. First, we have Professor Olexandr PETRENKO from the Dnipropetrovsk National University in Ukraine for the class today, and I hope this event will be enjoyable and worthy of knowledge. And for session for this event, we will hear presentation from Professor Olexandr PETRENKO, continue with Q&A session, and we will take a picture together. Yeah. Thank you.
Okay. Good afternoon to everybody. Just now I see that 14 our colleagues are ready to listen me. I'm sorry, but my web camera is broken just now, and I cannot repair it because war in our country is continuing. Today is 46 days after starting war between Russia and Ukraine, and the situation is very, very bad. But we hope to our victory. So, and I'd like to continue our presentation and discussion. I'd like to ask everybody if somebody has some questions, write please in chat, and I more detail focus it on these questions. But we will have some time in the end of today's our meeting for discussion and some questions and answers. So if somebody link it to our communication, I'd like first of all remind some aspects my previous presentation that will be more easy to hear and look a new presentation. So we discussed about presentation some approaches for creation automatic control system, which is presented in the form of space of states. Here is the main mathematical model. This is matrix differential equations. First equation is so-called equation of dynamic of system, and the next equation, this is equation of measurement. And also in frame of this approach, we also can look some random disturbances, which we presented as W. This is disturbances may be presented as output some dynamic system which is presented in such form. Last time we discussed about these mathematical models, and I said about new possibilities which we obtain in frame of this mathematical model. And the graphic presentation of this mathematical model is presented here. Here is this mathematical model dynamic of the object of control, and here is mathematical model of random disturbances, which is influence to our object of control. And we need create some closed system that for our object of control obtain some dynamic characteristics which we need, and maximal compensate influence random disturbances on the object of control. And here we, in frame of this approach, we discussed about some criterion of and some term of the controllability, and we discussed that the criterion of controllability is such presentation rank of matrix controllability must be equal n, where n is the order of system. So, and in frame of this approach, we discussed that the law of the control is presented in such form, where K1 is matrix of feedback signals, which give us possibility obtain the dynamics characteristics of the object control which we need. And K2, this is matrix of feedback, which give us possibility maximum compensate influence random disturbances on object of control. So, and graphically, such closed automatic control system is presented here. So you can see here matrix K1, which use vector of state of object of control, and matrix K2, this is also matrix feedback, which use signal of W, the random disturbances which are influent on the object of control. And here we discussed about two approaches for realize such law of control. And we say about two approaches. This is the first of all, this is approach of task of model control, and the next approach, this is creation the closed system and define the matrix of feedback on the base decision of the algorithms and approach of creation system of optimal control. And some recommendation for which we need to obtain characteristics, polynomial characteristics of closed system. We discussed about some approaches for obtaining these characteristics polynomials. So, and last time we also discussed about more detail, which is form of mathematical model of random disturbances, which, for example, we are presented it as the sum of some random steps, some linear elements, and some quarter elements. And for such, for example, presentation of the random disturbances, we obtain such form in the system of mathematical model, which we can present it as sum in some matrix form, where the matrix were obtained here. So, and this is some very briefly which we discussed about automatic control system last time. And when we discussed about some approaches for synthesis of closed system based on the problem of model control and analytical design of optimal control, we need to have some detailed mathematical model of object of control, and we need to obtain some mathematical model of random disturbances. But also, and here you can see we need matrix A, B, C, E, F, and the matrix D and H, which presented which mathematical model our object of control we obtain in the process of parametric and structural identification. But in the law of the control, we use vectors X and Z. And I say that last time that these vectors, as a rule, are not available for direct measurement for real automatic control system. And therefore, to implement the considered control loads, it's necessary to include so-called an observance service device into the closed system. And in the law of control, we can use not measured vectors X and Z, but we can use for these goals estimation of vectors. This is this one and this one. This is not real measurement vectors, but the estimated vectors. And in frame of this approach, in modern automatic control system, we need to understand the determine of the concept of observability. So the system has the property of complete observability when having mathematical model 1.1, it's possible to construct some dynamic model. This is observance service device, which will provide an estimate of the state vector of the system, X estimated. The criterion for complete observability of system 1.1 is the equality of the rank of its observability matrix Q observability to the order N of the system. This is the form the same as the term of controllability, but here we must to obtain matrix observability, which is presented in such form. And we can demonstrate, for example, a system which is presented in figure 1.3 has this system the property of complete observability or not. And the matrix of observability for this system has the following form: C, CA, CA quarter. Using the matrices A and C, which we obtained in example, for example, 1.8.1, we have matrix C is in such form, matrix CA in such form, and matrix CA quarter is such form. So we locate this matrices here in some more complex matrix, and we can see that this matrix rank of this matrix is number 3, because the determinant in such form is not equal to 0. So it means that the system which is presented in our example have the property of controllability. So just now we need describe some approaches to create this observing device. If a mathematical model of the control object of the form 1.1 is known, matrices A, B, C are defined, then the digital or analog model of the system can be considered as simplest observing device in such form. So we use absolutely the same mathematical model as object of control, and instead of matrix X, we use here estimation of this matrix X with this star. So, and the vector of control signals is used in the object control and the parallel to the estimation device. So the most simplest observing device can be presented in such form. So we have our real automatic controls, object of control with matrices A, B, C. And when we use the same mathematical model in such form and put here the same vectors of control signals, we hope that output will be same in real object of control and its mathematical model. And from this observing service, in this observing device, we can measure estimation vector of X. So as a rule, I ask for my students how will be this observing device working if we start real operation, our real system, and put these signals for some mathematical model in digital form of an analog form. It's anywhere. So, and most of students in my university answered for me that it's very good idea is as we have information about digital numerical values of matrices A, B, C, and if we realize it in our observing device, we will obtain corresponding signals. It's interesting for me how just now everybody who is take part in our meeting think about this idea. Maybe somebody want to answer for me or not. Okay. So since the observing device contains the exact mathematical model of control object, the same control signals U are applied to the inputs of the real object and the observer. It can be assumed that the state vector of system X and its estimate and output of observing device X estimation will coincide. In reality, this vector not coincides. This is absolutely impossible because the control object and the mathematical model have different initial conditions. And we cannot, for our this simple observing device, initial states as the same as in real object, because we cannot measure vector X here. So, during the creation of observing device, it's a problem that we cannot reference it to observing service initial conditions as the same condition in real our system, and therefore the vectors X and estimation vector X will not coincide. So instead of observing device shown in figure 2.1, an asymptotic observer is used. So I'd like that everybody good understand why we cannot use the observing device in such form. First of all, this is about impossible to organize here in the observing device the initial conditions, the same in real object, because here we cannot measure it. So, and just now we need look some new approach as some asymptotic observer. So to ensure that estimate of state vector of the system of the observer tends to state vector of real system X, an asymptotic observer is used. The principle of operation of such of observer is as follows. The vector of output variables of control object Y and the observer estimation y is equal c estimation x are compared, and the magnitude of the signal difference of the form in the negative feedback signal through a matrix L is fed to the observer's input. And corresponding, the mathematical model of the asymptotic observer has the following form. You can see here is presented the mathematical model simplest of our observing device, but here is additional member of this form. This is difference between real output of system and estimation of output in observing device. This is difference. And through matrix L, this signal is put as on the input of our observing device. And the matrix L ensures tends to X estimation to real X. The block diagram of the asymptotic observer is shown in this picture. You can see here, I'd like to repeat, here is our simplest of observing device, but we use here estimation output, and this is real output, and difference of these signals through matrix L put to the input of our observing service. So this is the observer's feedback matrix L determines the rate of the process of estimation, the state vector of system, and thus to creation an asymptotic observer, it's necessary to know not only the matrices of mathematical model of object, mathematical model of object ABC in form matrix presentation of mathematical model, but also to determine the values of the elements of the matrix L. To determine the observer's feedback matrix L, we represent expression 2.3 in the following form. We change previously expression in such form, and you can see here is some member of dynamics of observer, and here is two signals which is putting to the input of our observing. It's known that the condition estimation matrix X tends to real matrix L will be fulfilled if the observer is as a closed dynamic system. This dynamic system must be stable. So, and to determine the numerical values of the elements of the feedback matrix L, it's necessary to equate the characteristic polynomial corresponding to the closed system equation 2.4 to some desired characteristic polynomial. The same as we look last time for task of model control, we must look the determination matrix Si minus A minus LS C is equal to some desired characteristic polynomial. So here is S is the Laplace variable and I is identity matrix. From expression 2.5, we obtain a system of algebraic equation for obtaining the elements of the matrix L. We can say that the matrix L of the observer is determined in the same way as the matrix of feedback coefficient K in determined when solving the problem of modal control of the closed system. So, having created an asymptotic observer, the obtained estimates of the state vector of system X we can use in the control law 1.4. So this is the main idea. About creation of observing device. We need to create some closed system which ensure for us to obtain some estimation vector x which tends to real vector x in a real system. So this idea about creation of observing service device is can be some developed in the form the extended observing device. In control law 1.4, along with the state vector of system X, the uncontrolled random disturbances which act into the object of control W is used. And that is why we also need not only estimation vector of the X, and also estimation vector W. And that is why we need to create some observing device which ensure us possibility obtain both of these vectors. This problem can be solved by constructing an extended observer whose mathematical model has the following form. So you can see here the more complex matrix state of the observer, which it consists not only from vector estimation of state system, but also vector of state disturbances. And here we use not only matrix L and here in matrix L1, but we put here also elements which are connected to our disturbances, and we need to use the next also matrix L2. But the form of this observing device is the same as we looked some early. So here matrices L1 and L2 are the observer's feedback coefficients matrices, which ensure that the estimation error of the object state vector and the state vector of random disturbances tends to 0. To determine the numerical values of the element of the unknown feedback matrix L1 and L2 of the observer, we write down the characteristic polynomial of the observer and equate it to some designed characteristic polynomial. The approach is the same. We create some closed system and try to formulate some characteristic polynomial of this system and equate it to some desired characteristic polynomial. The equation for estimation error of the variables x and 0 for the observing device has such form. So this, excuse me, this is form for errors of the vector of state system of vector of state disturbances. And the characteristic polynomial of the observer, in this case solution, can be presented in such form. This is determinant, the corresponding this matrix, and it's equal to some characteristical polynomial. Equating the coefficient of characteristics polynomial of the observing device in this form 2.8 with the coefficient of some designed characteristic polynomial, we obtain a system of equation for determining the unknown elements of the feedback matrices of the observing device L1 and L2. Approach the same, but this extended observing device needs more complex procedure of determine the matrix L1 and L2. The structure of the extended observer and the scheme of its connection to the control object is shown in the next figure. So here we can look. This is object control, which is presented in form of matrix ABC object of control and matrix D, F, and H mathematical model of random disturbances. If we obtained it in procedure of parametric and structure identification of control system, we create this part of observer is for obtaining estimation matrix X, and here this is part of observing device for estimation random disturbances V. So if we connected this extended observer to our real system, we can take from here some estimation of matrix X, and we can take from here estimation of vector W. Here is presented process only estimation and observing, not use these signals for creation closed system for our object of control. This is a picture is for is presented only approach to realize this extended observing device. So here in this point, we can present the results of digital modeling of a system closed in terms of the state vector. So when solving the model control problem described in point 1.3, the matrix K1 is determined taking into account the recommendation for choosing the desired characteristic polynomial presented in point 1.4. In the process of modeling the system considered in the example of point 1.8, elements of feedback matrix K were obtained for the binomial form of the characteristic polynomial Butterworth and Bessel-Thompson. For each characteristic polynomial, the elements of matrix K1 are obtained for three values of the distance of the closed system poles from the imaginary axis, excuse me, distance I take 4, 8, and 20. So the results of digital simulation are shown in next figure, which we presented in form 2.4 and 2.6. The dynamics of closed system was estimated from the curve of the transient process of the system from non-zero initial condition of variables x1 from 0 on the system. So just now we can say, we can look in this picture. We can look in this picture. So here is results of modeling closed system, which is presented in my example. And when initial condition for variable x1 is non-zero, for example, 1, and after that, system is moving from this condition to stable state, which is equal 0. So if the distance from imaginary axis is different, you can see the speed of moving these variables from non-zero condition is different. So is very slowly process, and here is more quickly, and here is most so quickly. So if we change different distance our poles of closed system from imaginary axis, we can obtain different dynamic characteristics of closed system. So this is one for binomial characteristics polynomial. But this closed system is not the best because the process is very, very slow. So more quickly, closed system is operating at the using the Butterworth characteristic polynomial. You can see here the distance these poles from imaginary axis is the same, and you can see the character of process moving from non-zero condition to zero is the difference. But here we have some oscillation. And this is not very good in some practical realization. As a rule, I say and try to explain for my students, for example, if x1, this is altitude of the plane, and this is process of landing. And if we will use Butterworth characteristic polynomial, this is not very good when our plane will be meet with ground here in this point, and this point. So, for example, for landing of the plane, maybe the binomial characteristic polynomial is the best because it's very, very good in landing for plane. But for Butterworth characteristic polynomial, maybe this is we can use it in another task. For example, maybe in some speed, find some goals in the ballistic missile, for example, finding and so on. But the next step, I'd like to present you some results of modeling dynamic characteristics closed system for Bessel-Thomson characteristics polynomial. You can see at the distances poles of our system from the imaginary axis, we can obtain the dynamic process without any some oscillation. So last time I say that task of the model control, it needs to use some process of modeling and check which result we obtain during our process of synthesis of closed system. And you can see here, this is a demonstration that these pictures give us possibility to best understanding which we need to choose some recommended characteristics polynomial for every practical application. This can be binomial characteristic polynomial, Bessel-Thomson, Bessel-Thomson, Butterworth, and other approaches, and it's very strongly connected, which we need to obtain some dynamic characteristic for real application. So the simulation results show that, as expected, a closed system with a binomial form of the characteristic polynomial has a minimum speed. The system with the Butterworth characteristic polynomial, the next figure 2.5, has a higher speed, but the transient process is oscillatory and overshoot appears. A closed system with Bessel-Thomson characteristic polynomial figure 2.6 has a maximum speed with virtually no oscillation and overshoot. By changing the degree of removal of poles of closed system from imaginary axis, one can obtain the required values of system speed. So, in this point, we can look and understanding the process of modeling, the process of estimating the state vector of the system by the asymptotic observer. In section 2.4, we look at technique for construction the asymptotic observer and an algorithm for obtaining the numerical values of the feedback matrix L of the observer as a closed system. In the process of modeling an asymptotic observer for the system, considered in example of section 1.4, elements of the feedback matrix L were obtained for the binomial forms of characteristic polynomial Butterworth and Bessel-Thompson. It's presented in figures 1.7 to 2.9. For each characteristic excuse me, just now. Excuse me, electricity is turned off, so we need some. So, for each characteristic polynomial, the element of matrix L are obtained for 3 values of degree of distance of the system poles from the imaginary axis Q is equal 10, 15, and 20. So, here is presented the dynamics of the observer was estimated from the curve of the transient process of estimating the variable x1 with 0 with star of the system under non-zero initial condition. So here is presented the variable of x1 from system and the x1 estimation for different distance poles of observer is presented here. And in the initial conditions in observer was referenced as 0. So just in this picture, the dynamic of observing process for binomial characteristic polynomial of the observer device is presented. So this variable of object is changed in such form, and the estimation, for example, x1 start and it's moving for value of x1 real, reach it, and after that it decreases. So this is, you can see how the observer unit, observer device try to obtain the estimated values of variable x1 for a real system. So in this picture, the process of dynamics of observing process for observers Butterworth characteristic polynomial is presented here. So this, you can see the process of observing is more with more oscillations. And you can see for different distance poles of observer device from imaginary axis is 10, 15, and 20. So this is process not the best as here. You can see here the binomial characteristic polynomial is better for estimation. And here you can see the dynamics of observing process for observers Bessel-Thompson characteristics polynomial. You can see the process is the same as binomial characteristics polynomial, and if our system has x1, x2, x3, and another variables, the same process of estimation is realized in such form. Here I take only simplest pictures for our presentation for better understanding how the observing device is working. So you can see from these pictures that if we create observer device as closed system, and when we define numerical values matrix feedback L for feedback for observer device, we can obtain some better or worse process of estimation our variables in real system. And after that, we can use this estimation of vector of state system use in lieu of the closed system for real automatic control system. So next step is here I'd like to present you some process modeling, process of estimation random disturbances acting of the just excuse me please, I'd like come back here. What I forget say about some specific here. You can see here the distance of poles of observing device is 10, 15, and 20. And here you can see we look that distance poles of closed system is 4, 8, and 20. So it's very important. This is very important, and I'd like underline just now that for best application of observing device, it needs that poles of observing device must have big distance from imaginary axis than the closed system. So it means that observer device needs to speed of processes more bigger than in closed system. That these requirements ensure for us that results of estimation our variables will be obtained when the closed system needs these parameters. So And in each recommendation, which you can get in different books and some reference books, the distance of poles of observer system, observing device must have big distance for S than in closed system. And just now, they simulate the process of estimating random disturbances, action on the control object, the mathematical model of the extended observer 2.6 was used, the block diagram of which has shown in figure 2.3. When studying the dynamic of the process of estimating random perturbations, signals were applied to the input of the object, which were combined of stepwise and linearly varying signals that corresponded to real perturbations of the wave structure acting on control object. The simulation results of this situation are shown in next figures 2.10 to 2.12. So here is presented the results of modeling dynamics of disturbances estimation process for binomial observer characteristics polynomial. So what's here is presented, the variable z, which is in linear form in some step, and also linear form. And its results of modeling, when we put to our object of control such real disturbances. And here is presented correspondent estimation of this variable z. So this is the same zero state initial condition, and after that our observer try to estimate it. So you can see here is some error of estimation. When we have linear part of disturbances, and our observer try to estimate it during some time. Here is step of our real disturbances, and here our observer try to estimate it, and here it's very sharp to estimate it. Here also step of disturbances, and here our observer try to estimate it, and after that is moving here. So you can see that if we use some binomial observers characteristic polynomial, the process of estimation is in such form. So if we use Butterworth observer characteristics polynomial, here is the process is the same, but here you can see some oscillation during the estimation, but in some time we obtain the same estimation parameters, And here, the next picture, you can see the dynamics of the disturbances estimation process for Bessel-Thomson observer characteristic polynomial. And you can see the process is very, very quickly. in the form is the same to binomial characteristic polynomial, and some change from Butterworth characteristic polynomial. So you can see any characteristics polynomial give us possibility to obtain the estimation parameters which corresponding to real disturbances, and we can use it in our law of control. So this results is show that we can obtain the estimation of random disturbances which are acting to our object of control, and the results of this estimation give us some error, but we need we can use such parameters of matrix L that this error will be too small. So and this point 2.9, this is a point simulation of the closed system operation under the action of random disturbances. To simulate a system closed in the terms of the state vector under the action of random disturbances, we will use the mathematical model of a closed system, figure 1.2, and the mathematical model of an extended observer, figure 2.3. The results of simulation of a closed system under the action of random disturbances are shown in figures 2.13 and 2.15. So here you can see some dynamics of closed system for binomial characteristics polynomial and the advanced observer. So you can see this is results of modeling some real system. I model in some ion process in electrical propulsion thruster, which is working under some random disturbances. And for example, zero level, this is nominal regime of this real system. And when some disturbances is acting to a real system, advanced observer give us some parameters of vector, estimate vector of condition, and also estimate of these disturbances. And by closed system, we are compensated it. And you can see there is some period where our observer is operating, but after estimation, after process of estimation, closed system give us absolutely zero error. After that, the next period of estimation, and after that also absolutely zero of error of output variable. So, and using by application different kind of matrix K1, we can obtain these errors in some very small level. So here you can see also the same process of dynamics of closed system for Butterworth characteristic polynomial and the advanced observer. Here also you can see the process of observing. During process of observing, we obtain some error, but in some period we have very high level of accuracy of operation our system. But Butterworth process, Butterworth characteristics polynomial give us some process of oscillation in estimation, and it gives us some big errors. And here you can see for Bessel-Thomson characteristics polynomial, this is process is very good as for my opinion. So just now here I presented here some materials which I use for prepare these materials. Here is books very detailed discussed and presentation about some mathematical aspects of application, some ideas. And if somebody will be interested and for future application in these books, you can obtain answers to most questions which you will need to discuss and answer it. So just now this part of my presentation is finished, and just now I'd like to obtain some questions which you need discuss, and we have some time for discussion and maybe some comments, discussion, and some discussed about aspects which I present today, maybe last time, 1 week ago, and so. Thank you for your attention, and in chats I'd like to look just okay. So here is the control role in the company. Is okay. Okay. If I write to understand your
yeah, thank you, sir. We have 2 questions in room chat. Yeah, you can see it.
Okay. Thank you. I look and okay. Just now I try explain. So as some organizers of our meeting presented me, I am working in Dnipro National University in radio automatic control system department, but more than 30 years I worked in area of design, testing, and application, so-called electrical propulsion thrusters for space application. This electrical propulsion thrusters, this is thrusters with small thrust, and it used in satellites for keeping parameters of orbit, some orbital maneuvers, and maybe transfer from some orbit to another orbit. And our electrical propulsion thrusters includes in some so-called electrical propulsion system, And this system consists of thruster, feed system, which put some working substance to our thruster, and automatic control system. And automatic control system, it includes some program processes. This is turn on, turn off, measure some parameters, created some telemetric information, but it includes some closed systems, which used for keeping the level of the trust our system with very high accuracy. So, and these approaches which I presented here and today and 1 week ago, we use these approaches for creation closed automatic control system. And in frame of this approach, we realize some system of stabilization, level of the trust, this thruster, because some error of level of the trust give us very bad errors for parameters of satellite. So this in company in which I am as scientific consultant, I prefer these approaches for realize some real system. So, and I think this approach give us very good results. So I can more detail explain in which real programs this approach was used, but I have not previously information about interest students or some teachers of your university to my approaches. So, I'd like if we can realize next our meeting. In the next meeting, I'd like to explain how we realize such approach by using some digital hardware. Okay. So if this just now I look about letting removing noise error from many sensors in the tool. Okay. So as for noise error, for the noise error, this is just I try to formulate my position for it. So random disturbances. We can look in very wide range. Just I try to answer to question about error from many noise error from many sensors. So as for noise, noise error for sensors, we have very high level theory of filtering. different kind of digital filtering. It's very high and wide range approaches for filtering. And but the random disturbances very often differ from noise. This is, for example, if you move in some road by car, the state of this road can be give us some disturbances as noise, but sometimes is very slow but very high level change, level direction, and also. And in real automatic control systems, the influence of noise can be compensated by using different kind of filters. But if the level of random disturbances which reach, for example, 15, 20, 25% from the reference level, this is more difficult. It's impossible to compensate it by some filters. So, as for my opinion, noise errors must be compensated, must be minimizing using some filtering. It's maybe sometimes very simple, for example, integral link, maybe it can be filtering some noise. But our approach for observing unit, this is oriented to disturbances, which is described as the disturbances of waveform. And here, just now in this one, just now. In core books and Quakernack book, this is disturbances is described as disturbances in waveform. So let's, okay. So what, have you some questions?
I think we don't have no more questions, sir. Pardon?
Okay, if somebody interesting, I'd like maybe in couple weeks, I'd like to present for you some information about approach to realize such closed automatic control system using some digital units, if it's interesting. But I'd like for your students and teachers to catch your attention for some new possibilities which give us the approaches for creation closed automatic control system using approach of idea model control and creation optimal control system using observing your devices. And also, I think that using the mathematical model of random disturbances is very good idea for realize some closed system with very high accuracy. So here is I have not enough time for presentation. For example, here is very interesting question about correspondent mathematical model observer unit and the real parameters of object of control, because never we can to very sharp know mathematical model object of control. We have anytime we have some errors of determine the parameters of matrix A, B, C, F, G, and also I'd like to explain you that idea of observer device is compensated these errors. So, but we have not enough time for this discussion about that. So if somebody interested in it, I'm ready maybe in couple weeks continue our meeting and we can discuss about that questions. Oh, have you? Okay, can you send material before? Okay, this is yes, I agree with you. I'm ready present my materials for maybe somebody can look it before our meeting, and you can better and prepare some questions maybe. Yes, of course. So.
Yeah, thank you for Professor Olexandr Petrenko for their information will be beneficial audience, and I hope we can meet again at other event in the future. Yeah. So unfortunately, we already way off the time until last session. So sadly, and we would like to say thanks again for Professor Olexandr Petrenko. Yeah, thank you for sharing your knowledge with us. It's a very beneficial, and I hope we can meet again in future.
Okay. Thank you very much for your attention.
Thank you for Professor Olexandr. Yeah, goodbye.
Okay. Bye. Thank you very much.
Yeah, thank you so much also.
So.